Hello, my fellow programmers. Welcome back once more to this animated PLC course. Today we're analyzing our physical memory and our virtual memory. It's a pretty simple topic, but it's also very important. Now, let's start it off. So, physical memory. These are the devices, whether they're for input or output, that are tangible. Everything that we had seen before this are all physical memories. So these are assigned memory spaces in our PLC for physical devices, sensors, valves, inputs or outputs. Everything that is being connected. And these are all assigned memories for these devices. Inputs, outputs, analog inputs and outputs, which are also physical memories. Now, virtual memories. These are assigned spaces, memory spaces in our PLC. But these are not necessarily assigned for those connected devices. Now, what do I mean by this? This switch, so that we can identify it, what do we need? It's directive as I semicolon 0.x, wherever we're going to connect it. Virtual memories cannot have this type of directive. It's going to depend on each brand. They help us run simulations in real time. That's the advantage of using virtual memory. Now, let's suppose that we're going to program or we're going to run or start a big induction motor. Let's say 50 horsepower. Now, we don't want to make any mistakes, right? So we know that that's what this course is for. That's what this application is for. We already have our processes. However, a little bit more seasoning while on the field. We want to run tests for this big induction motor. So we can take certain memories and start simulating to avoid any errors or mistakes. So we take this physical coil and we can replace it for a virtual memory, just so that we can see that that virtual coil is being correctly activated. Just so that we know that we're testing these correctly. Okay? Now, these types of tests are the ones that are going to help us in our simulations. Now, I'm going to show you this in a little bit so that we have all of our concepts clear. So they help sending and receiving data in automatic devices. If we have a reading, for example, in our thermocoupling or a temperature sensor, it's going to give it to us in Celsius. And also, if that reading we wish to share to another PLC, so that it takes that information, which should work for something, and it's going to depend on the process. But let's suppose that process number 2 depends on that temperature information to indicate that our temperature, assigned temperature, is done for a certain temperature or certain values. And if it's done, it may need some other information to move on to the next process, or depending on what the customer needs. Now, many times we need that information or that analog data, or for times, and we need to share them with other PLCs or another PLC. Those of you who are a little bit more advanced can say, well, we can get that through Ethernet if we have everything connected, etc. Yes, most times, but what would happen if that more specific, if that information was a little bit more specific? For example, what happens if for physical memories it's not allowing us to run that description? Now, what would happen if we need to communicate a certain brand PLC to another brand PLC? Communication is open to get for PLC number 2, for example, over what PLC number one is reading. However, there are ways to communicate, for example, through messaging, and we can send virtual memories that are copying the information through physical memories. And those virtual memories, I can go ahead and move them down from PLC to PLCV. And also structuring databases. Now, since virtual memories are friendlier and we can start testing them at the moment of configuring or setting up that memory because they have different nomenclatures. However, they are more viable or feasible for us to assign names and for us to assign different data types. So we can start framing them in one only listing. And that listing, which has been focused on them, I can also share through my HMI or my SCADA system, something that is monitoring all this process, so that it can also get all this information again, not directly from inputs and outputs, but that it actually needs virtual memory to share, and that way we can visualize them. That's the big thing, basically. Everything related to virtual and physical memory. Now, let's look at some examples so that this is much clearer. Once you have a little bit more experience, you'll start noticing its advantages. For now, I need to indicate what their global advantages are. And then it's going to make more sense, much more sense. All right, so let's get to that. We're going to analyze with our Animator PLC or PLC Animated so that you guys can start solving your own exercises because many times you're going to use these virtual memories. Now, once we're in our Animator PLC, we're going to identify what our physical and virtual memories are. On the upper part, we have all of our memories, all of our memory devices. From all of these, we're going to identify which ones are the physical memories. Which ones do you consider they are? Even if I sound like Dora the Explorer, I want us to learn well. Analog inputs, analog outputs. Okay? All right, so these are the physical inputs and outputs, or their memory devices, all bunched up. Virtual memories are D and F. Now let's analyze each of them. Input, two devices. Oh, sorry, all input devices. Outputs and their nomenclatures. Now, virtual memories. These are known as binary files, which is nothing more than an integer. It really is an integer data type. And that's why it's telling us their bits or their divisions from 0 to 15, which means basically 16 bits or 16 booleans. Now, if we analyze F, which is floating or floaters, it has a real data type. F is for internal or virtual memories, which is nothing more or nothing else than analog inputs or analog outputs. However, we're not depending on any physical device. Okay? So analog inputs, everything is decimal. Analog outputs, they're all decimal. Okay? Now, let's analyze its differences and how they might help. I'm going to select an exercise here. So let's select a Klaus machine. So for this, we're going to create here, we're going to simulate an output, which is this one here, this device. our startup, and our stop, 0. All right. Now we know what it's going to do. Okay, so let's simulate this. When I press my button or my input number 1, then it's going to maintain. And that's the only thing that we're going to do. So with button 0, we're going to deactivate this. Activate, deactivate. Okay? Now, this is my point. This is what I'm trying to get to, or what I was trying to say earlier, is that this we can pretty much simulate with a virtual memory. And we select it. We select our word, and we're going to select our bit, which is, in this case, is v dot semicolon 0 dot 0. And we're going to enclave this. Okay? Now let's see what it does. What do you think is going to happen here? We're going to continue using our inputs, which have not changed. This is a combination from physical to virtual memory. Now, also what I'm trying to say is I'm going to activate this, and our coil has been activated. And with this other button, we are de-enclaving it. We're deactivating this coil, but our physical output is not activating. But at least I'm simulating what might happen without the need of risking or putting at risk my output. Now, what would happen? Why are we doing this? At a programming level, on this, we start programming better. However, maybe not because we're so special on this or specialized with these topics means that we're not going to make mistakes ever. We are going to make mistakes, yes, and they're going to be less, but errors nonetheless. So to exclude these types of errors, maybe for more complex processes, we can do this. We can start simulating our movements, our automatic movements, our manual movements, and we can start adding our sensors by saying, okay, so step number 1, what are we going to do? And we go to instructions. And we can start simulating all this. So we need to include also our physical output, and we're going to include our virtual memory. Now, once we know that it's working correctly, then we can substitute our virtual memory for our physical memory, and we're going to be sure that this is going to work because our simulation is working this way. Okay, now, what is this for? Let's suppose that from all the programming that we've done and running all the drills and tests day and night, we get overconfident and we simply not add a stop button. Okay? We're going to start up a motor or a valve or whatever it is, and I'm going to say, well, I'm going to start this. It doesn't work anyway. Now let's suppose that we already have our process that's ready, only for testing. And if we start with these types of failures, even if it's one signal, it's going to give us more problems for our tests, our trial runs in front of our bosses or the other engineers. And what we wish or what we want is less problems. So if we get confused and for some reason it's not even the same as startup, and if I'm pressing my button for my startup, and supposedly I have programmed that my program is that my button, my power button is 0. And if I get overconfident with this, and I say, well, you know what? There's really no need for a virtual memory. Or, I don't know, maybe I don't know what a virtual memory is. and I just press this, and I press my start or my startup, and if for some reason we need to stop, and I say, well, you know what, it's not working, and I cause a big problem with this, watch out, guys, because in theory, this button should work, but it's not working because I didn't direct it correctly. But this was at a programming level. The more I try to stop it, it's not going to stop. So it's a delicate process, and I can't really stop it. So we need to be very careful with this. So we also need to ensure our emergency stops, which is the first thing that I was saying and that I always recommend. Safety and security always needs to be activated. However, if we don't have these precautions, if we don't analyze our program, and if we don't simulate before we start our process, we're going to run into big problems. That's why we're also using our Animator PLC. But even with this, once on the field, there's going to be certain situations where you're going to need to simulate. And also something before we end this video, so that we can also analyze other types of situations for our virtual memories, is our timer. This is a physical memory or a virtual memory. It's virtual, right? Now, we may depend on some physical components that we're adding, okay? We do depend on this so that the timer starts. But the accumulated time as such, or this preset, is this physical? This is virtual, as well as our counters. And these memories have already been assigned internally in our PLC. Our programmers already assigned them, and all we need to do is identify them. Even though we have an assigned physical memory or an input or an output or anything that is a permission, or after I finish, I need to activate a different output, or even if they are together, this is a virtual memory. These are virtual memories. They've already been assigned in our PLC. This is virtual memory. This one is a different virtual memory. Okay? These are assigned memories or memory devices assigned to physical devices. What do you guys think? I hope you guys liked this class. I hope this was useful for you guys and you have a different point of view related to these memories. So finally, we're done with our Animator PLC, our intro, okay, for industrial automation. Now we're going to start adding videos to this section as complements, okay? For now, we're going to analyze each one of our instructions to figure out what they're for, and especially examples, and examples ultimately, so you guys can visualize how these are going to work for your own projects. And also, especially so that we can start solving Animator PLC exercises and drills. Thank you very much, guys. Big hug.